Daniela, can we start now? So
Yes.
let's just introduce. So we are very happy to have Professor Daniela Calvetti from Case Western Reserve University. And so she is going to talk on probabilistic Bayesian/Bayesian inverse problems. And Professor Calvetti has been to India at least 2 times as far as I can remember. Right. So, and she has visited TIFR Center for Applicable Mathematics. Hopefully your visit was enjoyable to India. So, and over to you, Professor Calvetti.
Okay, well, thank you very much for the invitation. And yes, I did enjoy India very much. And I wish I could deliver this talk on site, as I guess we all wish this workshop had not to take place online, but so are the circumstances. So this is the first of 2 lectures on probabilistic inverse problems. And looking at the audience, I've decided that I'm going to start introducing the use of probabilistic methods in inverse problems in a way that even people who are not working in the area can jump on board. And so I will go through the development so that it looks supposedly natural. There are lots of details under the hood, but that makes it a very exciting area to work on. And I will end with some examples, some illustrating how well these methods work. And then tomorrow there will be another lecture, which is the part 2 of this, and Professor Somersalo will give this. And I think it will also show how these methods can be adapted to time-dependent problems. Okay, so let me. So why probability and inverse problems? I will say that when I started working on this area, the two were coming together, but the world was not really sold on it. Right now, it's much more normal to see inverse problems set up within a Bayesian framework. And the story is that it's a commonality of interests. So in inverse problems, what we usually want to do, and that's why it's inverse, is that we want to estimate some quantities that are behind the consequences or the measurements that we have. So we have indirect observations, and we're trying to recover what caused these indirect observations. And on the other hand, there is the world of statistics and statistical inference. Let's say in a nutshell here, is that people try to figure out what is the distribution, what is the underlying distribution of a random variable. And if one can only know a few realizations of it. So if I give you a sequence of numbers, and a realization from a distribution, and I ask you, what is the distribution? Well, you're supposed to do the best with it. So the problem, or what the glue that puts together inverse problems and statistical inference is that whenever we have measurements, there is always some sort of noise, and noise could be imperfection in the measuring device, could be also physical noise that is superimposed to the signal of interest. And we can think that noise is really a random realization from a distribution, which often we don't know, but we have an idea roughly what it could be. And also in general, this distribution depends in some ways on the quantity that we're interested in. So what we do in the Bayesian approach, which is statistics, let's say with a flavor, with a Bayesian flavor, is we want to develop a way or a methodology for approaching this problem of statistical inference using what we believe are, let's say, some traits of the quantity that we want to estimate. And that will take into account, let's say, our a priori belief, but also the input of the data, the measured data. So, probability. So now we have very quickly connected inverse problems and the probability. And now let's look at probability. So in probability, okay, if one wants to sort of classify, which is, something that people do tend to do, although the relations are more common than not. There are 2 different ways of thinking about it. One is to think in frequentist terms, in in the sense that we can think of repeated experiments. So you think that you have an experiment, you can repeat it over and over and over again, and then you get your clues from that. Sometimes that's impossible, like let's say nuclear disasters. Hopefully they only happens very few times, or you know, events that cannot be repeated. In general, they defeat this interpretation here. And then there is a Bayesian definition, or the Bayesian way of thinking about probability, and is that the probability is really there to model in a lack of a belief that the subject has, and at the same time, lack of certainty about certain values. So whenever we do not know for certain what, you know, what is the value of certain quantities, for example, the weather tomorrow, then we tend to resort to probabilistic interpretation of the weather. And that's where we get this, you know, 40% probability that is going to be, you know, raining tomorrow. And if we knew what the weather is tomorrow, then we wouldn't need probability. So we think of Bayesian probability as of what they call subjective probability, because it's the subject that takes on the uncertainty rather than the object. And this is something that is going to play a big role in inverse problems, because, you know, after all, the subject, that is us, the observers, we often tend to know more than we're ready to admit about the quantities that we want to estimate. So to introduce the subject with you know, an example here, let's take a sequence here. So I have a sequence of you know, several groups of 5 digits, and I can put it on the board or on the screen and ask people to continue, and if it continued, it could be continuing on the left or on the right. So depending on the subject who's being questioned about how to continue the process here, we could have 2 scenarios here. The first scenario is that, excuse me, the sequence, the first subject says, well, this looks like a sequence of a random sequence. There is no real way of connecting, no real connection between these groups of 5 digits. So resorts to the idea of modeling this as a realization of a random process. And one way of continuing it in a credible way, so putting, for example, 5 digits to the left of the first group, to the left of the 26, is estimating the frequencies of the different digits in each group, maybe even looking at the ordering, and then creating one random sequence. That's, you know, according to subject 1, that's the most reasonable way. And here we're not attaching any moral connotation to the way subjects approach the problem. It depends on their experience and where they're coming from. Then there is subject 2, and subject 2 may be well in a math department, and somebody with a very, you know, sharp memory here. And the subject looks at the numbers and remembers that really this is the continuation of the sequence of the decimal digits of pi. And so there is no hesitation here. There are in putting the first, the beginning of this sequence, so 3.14159, that's what almost everyone remembers, 3.14 for sure. And this, the continuation of the sequence then will come from, for example, a textbook or a website. And in this case, subject 2 does not have any doubt that his answer is correct. So subject 2 does not need probability to answer this question. And in this case, the answer has no uncertainty attached to it, because it's a certain answer and it could be right or it could be wrong. So that, in that sense, you know, we're saying there is no right, we don't know. I don't know where this a priori, I don't know where this sequence is coming from. It could well be an approximation of pi, or simply happen to be realization of a random process. So That said, and without casting any judgment on subject 1 or subject 2, we say that in Bayesian probability is a way of expressing the uncertainty of the subjects about the quantity to be estimated. Uncertainty sometimes is called lack of information. But now we take away, so we can use Bayesian probability for all type of inquiries, regardless of whether the phenomenon, the object that we're looking at is intrinsically stochastic or fully deterministic, because randomness is not a property of the object, but is a property of the subject. So subject and subjective are two terms that need to be clarified, because sometimes Bayesian inference has been accused of being arbitrary. There is the arbitrary and subjective are different things. You can be subjective and arbitrary, but in general, in Bayesian inference, what we want to do is we want to use arguments that are subjective, because the subjective is the one that sets a probability, but also defendable. So we should be able to explain why we are making such assumptions a priori. Let's continue on this road towards probabilistic inverse problems. And now let's get to the more, let's say, philosophically deep question of why should we, can we model deterministic quantities as random variables? This is a big, this is actually a deep question here, because some quantities are definitely deterministic. There is no distribution around them, but what changes, what makes them suitable to probabilistic interpretation is that we don't know what the outcome is. So we're looking at two experiments here. The first one is predicting the outcome of a coin toss. So there are two states. Now time comes in, and I can take a coin and say, I'm going to toss this coin, and I want to predict what the outcome is. Before I've made, tossed the coin, the outcome is a random variable. It could take on two outcomes. The state of the outcome contains 2 points, either head or tails. Now, the other is that I toss the coin, I put it on the top of my hand, but I keep it covered. At this point, either the outcome is either heads or tail, but I do not know what the outcome is. So the event is totally deterministic, but as far as I'm concerned, it still remains undecided because I do not know the outcome. So in both cases, it's justified that I use a probabilistic approach. If I take this point of view that probability is in the eyes of the subject, not in the being of the object. If there are any questions, please, feel free to interrupt me. So now let's look at inverse problems, and I'm going to use some sort of formalism here to define an inverse problem, and then take it into the stochastic world. So let's say that our inverse problem can be stated in general terms as estimate a quantity x from a certain space, h1, from observations b. So I'm going to call b the vector of the observations, and the link between the object that I want to estimate and the measurements, the observation that I have access to, is given by let's say functional form of the type b is equal to f of x plus noise. So we're assuming here that the ideal link from the object the topic of our interest, X, and what we can observe of it is given by this functional form X, but there is some additive disturbances, and right now I'm not quantifying what this noise comes from. Noise could be, interference in the measurement device. It could also be that the model, the law that is linking X to B is imperfect. So I'm going to lump in this noise everything which disrupts this perfect relationship between X and B. Now, noise, we said before, tend to be similar but different every time we repeat an experiment, and measurements are experiments here. And right now, since we don't know X, and given that there is noise, we don't know B either, we have three quantities that can be represented as random variable, B, X, and E. And I can relate them with the equation below, this equation here, where the only thing that I've done is I've used capital letters. And the capital letters means that now instead of looking at B as a realization, as a vector of numbers, this is going to be treated as a random variable. Same thing with X and E. So now we're talking about relations between random variables, and we're ready to formulate the inverse problem in terms of probability distributions, which is the proper language to describe random variables. So now let's go ahead and a very quick trip through probability. So we're going to say that, for example, the space H1, where we are, where X lives, is an n-dimensional real space. The number of the space of the observation is Rm, and we can describe probability distribution in terms of Lebesgue densities. So we're going to say that the probability, formally, that the probability that Y is in B, which is a subset of Rk, is going to be the integral of over B of pi y of y integrated in the y, and we're calling the this function pi y here the probability density, and it must satisfy two well-known conditions. One is that it cannot be negative, so it's greater than or equal to 0, real and greater than or equal to 0, and it integrates to 1. So now, often or always, when we're dealing with inverse problems and we have observation, we have more than one random variable. So let's take two here, and we see how we can describe the joint density. So we take two random variables, X and Y. X is in Rn, Y is in Rm. They play the role of our unknown and our observations, and we can define the joint density of X and Y. And by joint density, with the joint density, what we can do is we can express the probability that X is in a subset A and Y is in a subset B. So we're just, we want to see how, how likely, if you wish, it is that X is in A and at the same time Y is in B. And this is going to be the integral, the double integral of A and B of the joint of this function here, pi of X, Y, which is the joint probability density of X and Y. And this is going to be integrated in dx dy here. And there is this process here that is called the marginalization that is very important, because sometimes, actually often, we're only interested in one of these two random variables. But the reason why we're going through this joint is because we don't have any information about the probability of, about the distribution of X, but we do have access to the joint probability of X and Y. And so if I want to know what is the probability that X is in A, regardless of the value taken by Y, well, then what I do is I, quote unquote, I go through this process of marginalization, which means that I'm going to take this integral, the previous integral here, and instead of integrating over B in dy, I'm integrating over all possible, over the entire state space of Y. and which essentially marginalizes with respect to y. And what I get out of it is the integral of a of pi of x dx, which is really going to give me the probability density of x. So now, if I take, and maybe let me come back here, and now if I want to know what is the probability density function of x evaluated at x here, all I need to do is I need to take this integral here, and I fix x and I integrate with respect to y. So now, if the probability of x, pi of x is different from 0, so this is a constant here, what I can do then is I can divide through by pi of x, and there are ways of dealing when, in the general case. And what we do is that by dividing both sides of the previous identity, we get that this ratio, the integral of this ratio is equal to 1. Also, the quantity, the ratio pi of x y divided by pi of x is greater than or equal to 0. So this satisfies essentially the conditions for being probability density. And we define this ratio here to be the conditional density of y, given that x has taken the particular value indicated here. So this is a way of linking three probability densities: the probability density of the joint density of x and y, the conditional density of y given x, and the density of x. So we've done this once, and there is no reason, if you go back, and I'm going back a second here, there is no reason why we should only be able to marginalize with respect to y. Of course, we could look at this integral here, and we can repeat the consideration that we made for x and for y. And by, let's say, swapping the role of x and y, we can come up also with a way of expressing the conditional probability of x, given that, given a particular value of y. So if we take the two expressions that the two expressions, and again, we're going to have the two expressions that both contain the joint probability density of x and y. So we solve for the joint from here. We solve also from the joint for from the condition of x given y. And now we set the two sides equal, and we arrive at this identity here, where we essentially, it looks like we're doing some magic of flipping back and forth between conditioning on x or conditioning of y, on y. And depending on what we know and what we want to find out, we can use this to infer or to come up with the probability density of x given y, in terms of the probability density of x, probability density of y, and the conditional density of y given x. This formula here, which is very simple to derive, I just did, is the well-known Bayes formula, although it was not stated by Bayes, but the Reverend Bayes is the one who actually came up with it. So this is a way of linking what we know with what we wish, and essentially we're moving things around according to what we have access to, which in inverse problems is very normal. So now let's make it a little more pertinent to inverse problems here. So let's look at this observation model. We call this an observation model. We're assuming that we have additive independent noise. So here, so E and X are mutually independent. in this model here. And now if X were given, so if we knew X, then the uncertainty in B would be only due to the noise. So that would be the only thing which would be uncertain. And which means that if X is given, and that's expressed by this conditioning given X, the probability density function of B, so we are expressing it in terms of probability here, is equal to, and now we have the inheritance law here, we have the probability density of the noise E, and this is going to be expressed, in terms of the noise, and the noise is solving from here, you see that is B minus f of X. Now this probability, this expression here is of linking these two probabilities is called the likelihood. This says how likely it is that we are observing data like B if given that X is, if X were known. Now, so this pertains the observation system, the data. And then there is another probability that will enter, and that is needed if you remember Bayes' formula. This is going a little bit fast, and I don't have, I can only show one screen at a time. But the probability, the density here, the conditional density is going to be multiplied by the probability of X. Now, what does the probability of X say? Well, the probability of X in inverse problems usually contains what or encodes what we know a priori about X. And now this is independent of the observation model, but is not independent, for example, of having solved the problem 1,000 times before or all of the literature that there is. So you can think that the probability of X is where we put all that we know, all the much or the little that we know. And this is called the prior. So likelihood and prior is what really are the main ingredient of Bayesian inverse problems. Now we connect it through Bayes' formula. So we go back to Bayes' formula, we make a substitution. X is playing the role of X, B is playing the role of Y here. And we say that, so in terms of inverse problems, I would say that the probability density of X, the unknown that I'm interested in estimating, given the data that I have access to, here we go, is given by the product of the likelihood. So I'm taking into account all of the uncertainty in the data that I'm observing. I'm multiplying this by the prior of X, which takes into account what I can say about X, independent of the data. And I'm dividing this, I'm normalizing this by how probable it is, the data is. So I may have a very unusual, a very improbable observation or a very typical observation here. And since I don't typically control the data, I'm just usually in inverse problems, we're grateful that we have data to solve our problems here. Since we don't have any control on the probability of B on the denominator here, which is fixed anyway, usually we say that the solution of the inverse problem, which is the way in which we describe our unknown, given the data that we have, is proportional to the product of the likelihood and the prior. And this is usually called the posterior. And in inverse problems, in Bayesian inverse problems, we usually say that the posterior is really a correction of the prior in light of the data that we have access to. And tomorrow, when you're going to be following part 2 of these probabilistic methods, remember this one. We start with the prior, data comes, we correct our a priori assumptions in light of our experience of the data. And this correction is what constitutes what we then can say about the unknown, and that's the posterior. Now, of course, if new data came, I would have to correct my posterior. Maybe, there is going to be another correction that's going to take me away. or if this is all the data that I have, this is really the complete solution to the inverse problem. So one thing is that the complete solution of the inverse problems in probabilistic terms is not a number, but it's a function. It's a distribution here. So now priors. Priors are difficult. Usually the prior part is, let's say, the one that is most novel to the people who are used to working on deterministic inverse problems. So let's talk a little bit about how one can express priors. And I'm going to take an example to guide me here. And so let's take a signal. And right now, let's assume that we're solving everything in a computer. So everything is discretized, so digitized. So the signal is measured. So G is measured at times Tj. And I'm going to call Xj the measurement. G of Tj is Xj. And I have n measurements. And then I want to estimate the signal from the data, given data. Now I have two models for the signal here. So I don't have the data, but I know roughly what the signal should look like. The first model is that I know that the signal always starts with the value 0. So x0 is equal to 0. And we also believe that the signal is such that at any point in time, if I take a tangent to it, the slope of the tangent is no larger than an m1, which is greater than 0. And that's one scenario. Second scenario is I have a different assumption about my unknown signal. I know, and here I have no probability, I know for sure that in the beginning and in the end, the signal is 0. And now I have also the belief that the curvature of the signal at any point in time is no larger than an m2 that is greater than 0. So now I start expressing what I know, and this is what, it's fascinating and sometimes frustrating about building priors. You have to take your knowledge and write it into some sort of way of encoding it in probability densities. So I'm going to express the slope. The slope is really in terms of the tangent approximation at, taking pairs of adjacent points. So this G prime of Tj is approximated by taking the difference between xj, xj minus 1, and dividing by the interval of measurements, which is h. And I say that the absolute value of the slope is less than or equal to m1. And I express it now as something that I say about the values of my signal. So I say that the difference between xj and xj minus 1 adjacent values of my signal in absolute value is less than or equal to h times m1. But right now I'm saying with some uncertainty. So same thing with the curvature. I write an approximation for the curvature of the signal at Tj. Now I need to look to the left and to the right, before and after point. And this is the formula for the curvature. And if I think that this curvature is bounded by m2, well, I can express this by saying that the absolute value of xj minus 1 minus 2xj plus xj plus 1 is less than or equal to h squared m2. And again, with some uncertainty. This formula, they look familiar, and this is no accident here. So in both cases, we don't know. So we are in a Bayesian setting, inverse problem setting. We don't know xj, so xj is a realization of a random variable. And now you see that the random variable here appears with the capital letter representation. So, and I have boundary conditions. So, we are in math here, we're gonna revisit our boundary condition. We know that x, by the way, it's not that big x. So when we're looking at a random variable here, we are thinking that the measure, so the value of the signal at each point where we have discretized it is a random variable. So we don't have a random variable here. We have, in theory, n+1 random variables. So x1, x0, x1, x2, xn. Now we look at how we set our boundary conditions. So we said that in the beginning, the signal is 0 with certainty. So meaning with certainty means that we scratch out the probability. So we really set x0 equal to 0. So we don't need any bars here. There is no room to play. Which means that really the only values of the signal that need the probabilistic models are the remaining ones, the quote unquote the free node. So x1, x2, xn. So in this case, in the first setting, same signal, but first setting, we really only have to estimate n values. Second setting, the beginning and the end of the signal is certainly equal to 0. And again, if it's certainly equal to 0 and I don't question it, then I don't need probability. It's just I set it. And which means that I only will use a probabilistic model for the remaining unknown. So in the second setting, I have n-1, random variables to estimate. And this is, so again, we're trying to express a prior here. We're trying to express something, say something about the signal before we have any measurements. And in the second case, the way in which we can model this, this a priori concept about the signal is to say that we will continue the signal by taking the next value, xj. So here we go. Xj is equal to the previous value, xj minus 1, plus a term here, gamma wj, where wj is follows the standard normal distribution with a 0 mean, and so it's a Gaussian with 0 mean and standard deviation equal to 1. And I'm using my idea about the slope here being bounded with almost, with some uncertainty by m1 by setting gamma to be equal to h times m1. So we're saying that, in other words, we're saying that the signal at the next step is going to be equal to the signal, should be roughly, I expect it to be equal to the signal at the previous position here, plus some innovation. So this is the innovation here. And the term which changes the value here is going to be, has some randomness because there is this W, so it could be very, very small. And they say 60%, 67% of the time, it will be, within one standard deviation. And it's bounded, so the amount of innovation is really guided by my a priori belief about a bound on the slope. So one can do it several times, and sometimes it will be up, sometimes it will be down. So a priori, I cannot say what the signal is. The data will then specify, but it's a behavior. Second, this is called the first order prior. It's also first order autoregressive model for those for which this makes sense. And then now let's look at the second scenario here. In the second scenario, I'm making a statement about a probabilistic bound on the curvature, which means that if I want to sort of make a prediction about, without data, about what the value of the signal would be at, let's say, the point xj, I'm making it not in terms of the previous one, so there is no causality here, but I'm saying that if I knew the values at xj at the previous location, the location on the left and on the right, well, according to what I've said about the signal, the value in the middle should be about the average of the two plus some innovation. And this innovation term here, again, is stochastic because it has probabilistic component. I'm drawing WJ from the normal 0, 1, and it's multiplied, it's scaled by this term here, which comes from the frequency of the measurement, so how far apart the different nodes in the discretization are, and the bound on the curvature. So these are two different a priori models, so the two different priors for the signal. The one, these are very well known, they're smoothness priors, and because they add regularity, so the signal cannot really vary. We don't expect the signal to vary dramatically from one value, from one position to the next. The first is called first order prior, the second order prior. And how do you know if you're saying the right thing or not? Well, let's continue. Second,
Daniela, can I ask a question? Sorry.
Sure.
So in the previous slide, right? So if J, if J is far away from the initial starting point, the errors can actually add up, correct?
No, these are not. So this is a local. I'm saying this locally. So I'm making this statement. Let's say I'm entering. Think that I have my signal here, and the question that this smoothness prior is answering is the following: I am here, right? What is the value? So what if I were at this position, let's say xj minus 2, what do I expect without having any data, the value at xj minus 1 to be? And I'm using a model like this. The only thing that I can say is that if I know that what I can say is that with this first order prior, x1 cannot be arbitrarily far away from 0 because I have the boundary, the initial condition, the initial boundary condition that is 0. And so that's going to be essentially, that's where I start. But then it can go up, it can go down. So if I'm, I can be very far from 0 after a while, but I've moved sort of every step has been pretty much, let's say, gradual and borrowing a little bit. And that's what I expect. Then I can have data that is totally in disagreement with this. That's, that becomes a controversy. So it's more
but
like.
On the other hand, yeah, please go ahead.
Yeah. So this is like. Sort of, I'm going to show a picture in a second that might clarify. So this is almost like writing. So we're writing for every point. And again, here we're linking together. So maybe that's the best way of saying it. When I'm writing this capital Xj and capital Xj minus 1, these are all random variables. So I'm relating I'm relating 3 random variables here. The random variable that represents the value of the signal at the current position, the random variable that represents the value of the signal at the previous position, and the Wj, which is a random variable that is independent of xj and xj minus 1. In fact, it's drawn from its own distribution here. And this is going to be the same in right now at any position. So this Wj is really could be simply a W. And that's the third random variable. And I'm saying, that I'm linking the random variable to its neighbor to the, let's say, to the left here, and to a stochastic component, which is Wj. And this will add some regularity to the solution that I don't know, to the signal that I don't know. And the more, let's say, the smaller M1 is, the more like xj minus 1, xj will be, because it cannot innovate all that much. This is, but it's done locally, so it will depend. So what xj is, what x1000, for example, is, will depend on what X999 is and what I'm saying about M1. It's only like the beginning. The beginning will put some hard constraint, because right now I'm saying that I do know the initial condition, that is 0, which I may not know. So that's, let me continue, because I have in a couple of slides, I will have a picture that I think, hope will clarify what's going on. It's also like, this is also going to be connecting this probabilistic way of thinking with very classic deterministic way of setting, regularization operators. So I'm going to write all of this down all at once in an economical way. So I write all of the conditions together. So x1 is really equal to x1 minus x0, because x0 is equal to 0. And this is going to be equal to gamma, w1, and then x2 minus x1. So I'm just collecting all of the conditions here. And well, these are can be thought of as, components of a vector of unknowns. So I collect all of the, let's say, unknowns to be estimated in the vector x. So this is a vector of, this is a, what is it? This is a vector of random variables here. And I can express the left-hand side here as the product of the matrix L1, first order, differencing here, find a difference matrix L1 times X. And if I put, if I make a vector with all of the W's, so this is a vector of n standard normals here in the vector W, then I can say that what I'm expressing right now about my signal in terms of this first order smoothness prior is that the matrix L1 times the vector X is equal to gamma, the scalar gamma, which was H times M1, times the vector W, where W is actually, it's really an n-dimensional standard normal with a scaled identity as covariance here. So now we're relating to first order difference in scheme. Now I'm going to do the same thing with the conditions that I'm saying about the signal in the second scenario, where we are so in a way constraining or linking the value of the signal to the two neighbors, the one to the left and the one to the right. It's the case where I have two boundary conditions here. So I'm writing all of the conditions at once, again, keeping in mind that x0 is equal to 0 and xn is also equal to 0. So I make the same considerations as before. I look at the x1 through xn minus 1 as my as a component of my unknown x. So now x is a vector with n components, and the n components are univariate random variables. Here, I write down the matrix of the coefficients which make the left-hand side here happen. And this is well-known, right, matrix L2. And then again, I'm collecting all of the right-hand side into a vector, which is a scaled white noise. And I can write the prior, which is expressed in terms of the curvature as saying that L2, the matrix L2 times the vector X with the n minus 1 component is going to be equal to gamma times W here. Now, at this point, we can take all of this to the computer, and we can look if the signals that I would generate according to this formula, let's say still unconstrained by data, because this is a prior, so I don't know what the data is going to be like, but we usually have a sense of what kind of solution we expect. And we want to draw, we want to, get some realizations. that tell us if we are on the mark or not, or even if we should use a first order smoothness prior, a second order smoothness prior. So what we had before is that in both cases, the prior was expressed in terms of L, a matrix L, either L1 or L2 times X equals W. And W was a scaled white noise of the appropriate dimension here. I can scale the matrix L so that I don't have to keep track of the gamma here. And I can write down the formula. After all, this is kind of like almost, look, it is a linear system. We can say that X is equal to the inverse of L times W. L1 and L2 were both invertible. And now X is a random variable. So I'm going to go through the formula for computing the covariance of X, which is the expectation of X times X transpose. And this is pretty straightforward to see that since the W has a covariance equal to the identity, the covariance of X is simply L inverse times L minus transpose. So the inverse of the covariance is usually called the precision matrix. And now I take the inverse of the covariance using its factorization here. And we get that the inverse of the covariance is L transpose times L. It's a really nice symmetric factorization of the covariance. It's also one that makes, which tells us how we go from a random variable X here to what is called white noise. And the reason why it's nice to know how to go to white noise is because white noise is encoded. We have nice software to simulate it. This transformation that sends that sends X to LX. And now if we go here, we see that Lx is going to be equal to W. So that's why the name of whitening transformation, also Mahalanobis transformation. So now we have, if we have this relation, we can draw white noise and we color it. So we go back and then we draw, and then we look at what X looks like. And essentially, this is all of the formula here, sampling from Gaussian densities. That's what makes Gaussian densities really favorite, because we can simulate them easily in computer. So this works in general. I'm going to skip this, and instead, I think this might answer the question that you had previously. I don't know, I hope it does. So these are different realizations of the signal X, modeled according to the first order prior, smoothness prior here, or second order smoothness prior. And again, these have been realized exactly according to the formula that I gave. And you can notice that in the beginning here, so when the signal is very close to X0, so values of the signal that are close to its left boundary points are small, because there is a bound on how much they can deviate from the previous value. So they start from 0 in the beginning. They will move, slowly away from 0. They don't all move equally slowly. This realization here, this blue, makes a jump fairly early in the positive direction. Some of this, let's say this magenta, goes in the negative direction, and every point I can, the innovation can be with a positive or a negative sign. Some signals, in the end, they are fairly far from, let's say, the 0 mean, in the positive or in the negative. And I don't say anything about how the signals should end. So this is really open, right? The first one. In the second case, and you see the difference between first order and second order. The second order smoothness prior gives us a much, much smoother signal here. And in this case here, I'm saying that the signal is 0 in the beginning and in the end. So this is, you see the effect of the boundary here. It's also, I think it's always a good idea to look at things, because we might have thought that second order smoothness prior would be great for, an inverse problems for modeling a one-dimensional signal. When we look at this, well, maybe what we had in mind will look more like this. So that's what would sort of give us a sense of, what is better. What is better is what encodes more closely what are our a priori assumptions or beliefs about the solution.
So Daniela, I have a question. So in the second figure, right? So this answers my question, but in the second figure, is my understanding right that because your xj minus 1 depends on xj minus 2 and xj plus 1. So
exactly,
and it is deterministic at the right end point. That's why you always have it actually going to 0.
Yes,
is that correct?
It's correct.
Okay.
And if it's not going to 0, of course, you could have a boundary condition here that puts it up. It could be going to 1, but it's always approaching where it's going. So if it knows, if it has to go there at some point and it cannot deviate too much, it will get ready to land there. Yes. Okay, so let me continue a little bit. So now we can, of course, this, I start with one-dimensional because I think, one needs to have, I always think that it's nice to have an example, a simple example to ground us that we can go back to every time the doubt strikes here. So we can actually come up with much more elaborated a priori belief about the solution. And so, for example, we could have a prior which is defined in terms of differential operators here. And so we can define boundary conditions in the same way, but now, we are in n-dimensional space, so things are a little more, intricate and technically more challenging. So we write different discrete approximation, which is what we have done previously in one-dimensional case. And examples of very popular and very powerful priors built in this fashion is what is known as the Whittle-Matern prior, that they are described in terms of the Laplacian here, the Laplacian, and the discretization is in terms of finite difference or finite elements. And in this case, the equivalent, so we have done a quantum jump here, the equivalent of the condition that we had before can be expressed by saying that we believe a priori that our signal X here satisfies this equation here. So now we have the minus d is the approximation of, is a discrete approximation of the Laplacian. And then we have this addition of lambda 1 over lambda squared times the identity. This is raised to the power beta. Beta is giving us the smoothness order here, and the coefficient, the scalar lambda, which is always positive, is called the correlation length. And again, this is white noise as before, and this is going to be scaled by gamma. And I'm going to give you a sense of what kind of patterns or what kind of priors we get if we assume that our unknown is governed, or a priori, the best that we can say about our unknown is that it should look like some of this realization from a Whittle-Matern prior. So these are several 4 realizations from these Whittle-Matern priors with different correlation lengths. In the top here, the correlation length is 0.05. On the bottom here is 0.5. And we had the smoothness parameter, beta equal to 1. And again, the reason why I'm showing this is because when you decide which prior, or you have to choose which prior to adopt, it's good to look at it. Because if you're solving a problem that other people have solved, or it's a physical problem, you may know that a priori, you may not know what is the solution. That's why you have data and you're solving an inverse problems. But you may have a pretty good sense that your solution is going to look something like this rather than something like this, in which case you would use a Whittle-Matern prior with a smaller correlation length. If you think that is, let's say, these lumps, these curves here are smaller, or you're going to go for larger. So these are, when you're looking for inclusions in X-ray, or small or large, this is when these Whittle-Matern are very convenient, because you can sort of in some way tune them to what your expectations are. These are priors, so the data then will correct your prior in light of the observations. Now let's add structure. So these are uniform in some ways, right? Except at the boundaries, we don't have many, say, breakpoints where things happen. So let's see what happens if we have a reason to believe that, for example, in a signal, at some point, there is an event where the curvature of the slope become much higher. And right now we've done a lot of actually Bayesian, I've personally been involved with a lot of Bayesian methods for predicting the number of daily cases of the COVID-19. And yeah, there are cases, there are times, like for example, holidays, when there is a reason to believe that the numbers will go up. And that's the equivalent of saying that you expect that in correspondence of some events, the usual, say, innovation will change and can become much larger here. So let's say that at some point we expect that the slope of the curvature are possibly as many as 10 times higher. If we know when that happens, like in the US, we knew that Thanksgiving and Christmas would be, pretty bad, then we can go ahead and in our prior, we can replace the condition, the usual condition, the usual, say, innovation condition here, with a modified one where we actually increase the gamma. So we increase the variability at that point by the corresponding factor here. What that does is it creates this, let's say, events here where you are allowing, right, the innovation to be higher. In this case, it was at 0.3 and 0.6. It's also to be noted that it's not necessary, because there is also a random draw from a normal, could be very close to 0, in which case the 10 would not have much effect. But all we're saying is that it is possible that this happens. And one can notice this, let's say, changes at particular points. And this is different whether we do it on the first order prior or the second order prior. So nothing is forced. And let's say, well, nice if we know this, like on the calendar, if you can go by the calendar, but in signals or natural phenomena, sometimes we really do not know at which point the change will happen, but we can have a priori, and again, this is all a priori here, the sense that it may happen at some point, but we don't know when, and we don't know, we don't even know how large this innovation should be. So we don't know which of these Ks we should modify, and we do not know by which coefficient we should scale the gamma here. So now we go back and we recite the mantra of Bayesian approach once again and say, haha, now it means that we're scaling the innovation here by a coefficient that we don't know. Anything we don't know in our approach to this probabilistic model is going to be modeled as a random variable. So we are going to go ahead and change, for example, this first order smoothness prior by introducing another variable, a random variable, theta here, and random variable because it's an unknown coefficient here. So we rewrite the conditions exactly as we did before, except that right now the white noise here is scaled by yet another, by a parameter that is really the variance of the Gaussian innovation. But since we don't know it, it's a random variable. And if it's a random variable, it means that we need to describe that also. And so we need to actually come up with a probability distribution that describes the theta k. So now, we are adding, as it often happens, one small modification and things become a little fairly complex. So let's go back to the matrix vector notation that is extremely convenient also to keep things, in blocks here. And let's write our first order prior as L or second order, because we could also have the L2 here. So let's write down our what we say about X in the form of Lx. L is a fully known matrix here. X is our vector of the vector of unknowns that we're primarily interested in. And this is going to be equal to W is white noise. And now we have D, the matrix D, actually the square root of the matrix D. And the matrix D is a diagonal matrix with entries, theta 1, theta 2, theta n. Those are positive entries because we have to take the square root of it. And because they have to play the role of variances here. So now we know what W. We know W. W is an n-varied standard normal, so we can actually write down is density. We have a formula for it, so we can write down the probability density of X by inheriting, like if we knew D in terms of W by solving this for W, by solving this for X in terms of W, and so that's right. Let me go back. I don't want to confuse more. So what we have here is that the density of X is inherited from that of W. I take W here. W is going to be equal to D to the negative 1/2 times Lx, and W follows a standard normal distribution. And that's what I'm writing down here. Now, again, if we have information about location, number, and expected amplitude of the jumps of these changes, we should use it. So probabilistic interpretation doesn't mean, being dumb. If we know something for sure, we're not going to estimate it. We're just going to encode it, like we did for the boundary condition. And if we only know of, as I said, as I repeat, we only know that we may have jumps, but we don't know how many, where, and how big, then we start thinking about how we model it. And first we make a wish list of what we would like, a probability density for these jumps, for these variances to encode. And then we look among the known probability densities that are also more let's say, better suited for computations. That consideration will come in a second. But first we need to write down what do we want from them. So what we want to express that is that the variance is unknown. It's a random variable, we've already said it. Okay. So in this slide here. So we are entering the estimation of the variance in the problem. So now we will double. So if we enter this uncertainty about bigger changes, we're going to double the number of unknowns, because we will have to estimate both x and the theta here. And we could write a prior, right? And we had it before. We have a conditional prior if we knew theta. And I had it, I think, yes, here, right? If we knew theta, it means that we knew d. We know d, L is known, so we can write prior for x. But if we do not know x and theta, what we can do is we can go for the joint prior for x and theta by passing through the conditional prior. So we can write a conditional prior of x given theta, and then multiply this by the probability density of theta, which in this case we call the hyperprior, because it's a prior for a parameters that enters in the prior. So essentially, we are interested in the joint prior for x and theta, because now these are our new random variables to be estimated, and we go for it in pieces, in the sense that if we have a convenient expression for the prior of x, if we knew theta, we write that down, and then we pay for the fact that we've gone through the conditioning by multiplying it by a probability density function that describes the uncertainty, or what we want to say about theta here. And now there are a few adjustments, because before we had because often we neglect normalizing constants that we do not control in inverse problems. And now, if we're using a prior for x, which is conditionally Gaussian, okay, and it's conditioned on theta, we cannot ignore the normalizing constant in front of the exponential in the Gaussian, because now this normalizing constant is no longer constant, but it's only constant given for a particular value of theta. So essentially, this factor here, and I put it in blue so that it can be followed. This factor here will depend on the matrix d theta inverse, and as the realizations of theta change, the prior for x, the conditional prior for x, will also change. So that brings up another problem, and is that if we want to draw some of this, so sure, we can draw the theta, and then we can draw the x, but we need to keep in mind that we have this normalization factor, so we need to compute the determinants, and computing determinants in particular for finely discretized signals, so large matrices, it can be complicated. So if the matrix L is invertible, we use the properties of determinant, and we can actually go ahead and compute it in analytic form. Otherwise, we have to start thinking about it. So there are cases in which we have matrices L that are non-invertible. And then in that case, again, to avoid heavy computations, or in particular computations of determinants, which can be very, very time consuming and unstable, what we can do is we can think about the signal in terms of increments rather than in terms of signal values. So if I have, and in a way, this is very natural, because when I was writing down before the conditions for first order and second order prior, essentially I discretized the signal, and I was looking at, for the first order prior, I was looking at the difference between the value of the signal at the current position and at the previous position. You can think that what I was doing really, I was expressing a condition on the increments of the signal as we move forward. So again, so we can go ahead and we can make changes of variables as appropriate. And sometimes we think in terms of signal, sometimes we think in terms of increment, and a lot of what justifies or what determines which way is best to think about an inverse problem and how to parameterize it is the underlying computational cost. So I'm not going through this. This is technical, but it will be with this slide. So I want to spend a little time, which let me see how I'm doing here. I still have, so I want to spend a little time dwelling a little bit more about this idea of introducing hyperpriors. And I want to give you a sense of how powerful this idea of introducing this unknown variance of this innovation can be if we use it in like in a smart way, because it can give us some for very, very cheap sparsity promoting priors that we can interpret, understand, and in the end solve extremely in a very, very computationally expensive manner here. So let me revisit, let me visit for a second the problem. So, and we're still staying with the prior here. So let's say that we have our inverse problem and we know something about our solution. We expect, for example, that we will have a signal that most of the time will be quiet or will be close to a background, but we expect that there could be a few discontinuities. So if you think, for example, of a sky, night sky, the sky, most of the sky will be dark, but we expect, if it's not a cloudy night, that there will be a few stars, but the stars are not many. And in general, we don't know where they are, but if we look up, we expect to see a few of them. So let's say that we want to encode this. Was there a question? If that was a question, I didn't hear it. If it was a disturbance, I will ignore it. So let's say that we want to encode this idea. We want to build a prior where, which tells us that there could be some sudden jumps, not many. So if we want the variability of the signal to be sudden, then it makes sense that the variances of the innovations are independent. Otherwise, we saw that with the draws of from the first and second order prior, if there is, if they depend on the previous one, well, they will be constrained. So we want the signal to be free to jump as much as it wants, or as much as we say can jump, but at any position. So we pretty much model the variances as independent. Then we don't know, if we truly do not know where the locations are of these jumps, then we would like the variances to be identically distributed. So whatever the distribution will be that will facilitate, make possible to have these jumps, but not many, it should be the same for all, at all locations here. And then when we choose the distribution, we should choose one such that most of the variances will be close to zero. And then zero can be then tuned to be close to a background. but they should not, we say that the signal should not, for the most part, deviate from a background, but it could have a few variances, very large, but only a few. So few in statistical terms should bring up the notion of outliers here. So in the choice of our hyperprior, we want, for the choice of our hyperpriors, we are going to reach for families of probability densities which are fat-tailed. And the fat-tail means that, without getting into the details there, it means that it's natural for these distributions to allow outliers. And how many or how few will depend on the particular distribution that we're choosing. And it turns out that if we're modeling, if we are having a Gaussian likelihood, which is actually a model that can cover quite a lot of ground there, then the gamma family of distributions is very nice. It's a very nice choice. It goes very well together with conditionally Gaussian priors and Gaussian likelihood in computational terms. So let's look at this family of gammas. And yes.
Sorry, Daniela, sorry to interrupt. So our next talk is starts in 10 minutes at 10 minutes from now.
Okay. So, all right. So these are the gamma distributions. So the two most useful are the gamma and the inverse gamma. And they satisfy exactly this condition most of the time. They will model variances that are close to zero, and a few times these variances will be very large. And so I'm gonna skip. So there is a whole part on very technical, on more technical, on the two-dimensional signals, so images, which have additional compatibility conditions, but basically, let's say the approach is the same. Again, we want the signal to be able to jump, the image to be able to jump. And so now let's go with sparsity promoter priors. I was talking about gamma and the inverse gamma. And it has been shown that the inverse, that the gamma hyperprior. So if we take a Gaussian prior with conditionally Gaussian prior with gamma hyperprior, essentially the solution to the inverse problems that we get is, and I will say akin, I'm skipping all of the details, but this has been proved, similar to what we would get using a classic, let's say, L1 regularization, except that everything is computationally more slender, and it can be done just in terms of solving least squares problems and let's say closed formula for the computation of the thetas. And so different priors here, different realization of this is a white noise prior, which would correspond to assuming that essentially it's you're drawing your solution from a normal. This is an L1 prior. So with positivity constraints, this is a total variation prior. And the only reason I'm putting this slide up here is because, again, if you're choosing priors, choose them for computational convenience, but also it should correspond to what you are expecting from your solution. Question, if we have, so I have just a couple of minutes, so I'm gonna just show a couple of results here. So let's say that we have additive Gaussian noise, and we have blurring a blurred image here. So we have the convolution problem. We are trying to recover an image of this type. This is a blocky image. We are recovering it from a blurred and noisy image of this type. So this is the width of the kernel, of the blurring kernel here. And we're using this with, so if we're doing this with these hierarchical priors where we are assuming that the increments, so here we're looking at the jumps in intensity of the image in the X and Y direction here are few. So after one iteration, this is what the image would look like, and this is what the thetas would look like. So after 3 iterations, this is the type of reconstruction that we get, and this is the thetas. So remember that the thetas will tell us where the big jumps are. So they're almost like a boundary. They are large where there are discontinuity in the image, and they are near 0 everywhere else. So we can almost see that the thetas, they identify the boundaries here of these images. And these are just very few matrix vector product and formulas evaluations. So it works quite well with images. And let me see what else. So these are the technical details when you're putting a Gaussian likelihood together with a prior. And again, in the prior, I'm writing it as a Gaussian, but you can have different components to it. And what one can do is one can also always go through the process of whitening everything inside. And what I was showing you as the image was not a distribution, because that would be, that would be a function, but I was showing you a single point estimator, so the maximum a posteriori estimate. So computing maximum posteriori estimate is usually a way of synthesizing a distribution. And in the case of using this Gaussian likelihood and conditionally Gaussian hypermodels with this gamma family is a way of making the solution, making the map maximum posteriori estimation really happen with the solution of a few least squares problem and a few formula evaluations. The reason for selecting to use iterative methods is given by going through considerations about how to compute solution with Tikhonov regularization. And right now, so there are sort of iterative methods. I don't want to eat in the next talk. Let me just go ahead and show some application of these hypermodels, priors built as sort of I went through for an magnetoencephalography problem here. Difficult problem because we have very few measurements and a lot of, let's say, a lot of nodes here, a lot of possible positions. It's a sparse activity, and the effect of the prior here is that depending on how much sparsity we expect, which is, in this case was controlled by one parameter, we get a very, very focal solution, or a little less focal. Again, this is real data. And by using this soul searching and the help of probability distributions, we can enter anatomical information. And we were able recently to get actually estimation of activity in the deep brain from MEG measurements that were then used to see what happens, or to understand whether the brain during meditation really changes or not. And this reconstruction here only required 19 matrix vector product altogether. And we had a problem with 57,000 unknowns and 305 measurements. And I will stop because I think my time is up. Thank you.
Thanks, Daniela.